Graphing polar equations. Now let's talk about graphing polar equations. Polar equations can be graphed by inputting angles and finding outputs that are directed distances. So just like if we have a function y equals f of x, we can substitute in x's and get out y's. Well, here we can substitute in angles theta and get out r values. So let's say we wanted to graph r equals 3 sine theta. We could create this r theta table and we could input angles. Let's say the typical angles between 0 and pi over 2. We could substitute those angles into theta to get out r values. So that's already been done here. So again, we started with theta values. We substitute them in. So sine of 0 is 0, times 3 is 0. Sine of pi over 6 is 1/2, and 3 times a half is 3/2, and so on. So after you create this table, then you have a bunch of coordinate points, polar coordinate points, and then we can plot those points, which has been done over here for us already. So the graph of r equals 3 sine theta looks like this circle here. And so we could think about the polar coordinate 0, 0. We go to the angle 0, and we wouldn't go anywhere at all. So that is going to be this coordinate point here. And then we'd go to the angle pi over 6 and go towards it 3 over 2 or 1.5. So here's pi over 6. And if we go towards it 1.5, that's going to lead us to this coordinate point here. So this is the point 3/2 pi over 6. And then at pi over 4, we get 3 rad 2 over 2. So pi over 4 is this angle here. And so we go towards it an amount of 3 rad 2 over 2. So it looks like that's going to be a little bit bigger than 2. So this is 3 rad 2 over 2, pi over 4. And then when we plugged in pi over 3, we got 3 rad 3 over 2. So that's going to give us this coordinate point here. So this is 3 rad 3 over 2, comma pi over 3. And then we get pi over 2, 3. So we go to the angle pi over 2. And from the pole, we go 3 units towards pi over 2. And so that's going to give us this point here. So all I did was actually plug in angles from 0 to pi over 2. But because of symmetry, we are going to get these remaining values here. And I'm letting you know that this is correct. It is going to graph a circle. And so here's the direction of motion for this polar equation. But that's kind of a lot of effort. Just like with rectangular equations or equations in x and y, we don't really want to plug in a bunch of x values to get out a bunch of y values. We want to start to recognize patterns. So here, notice that we have 3 sine theta, and this circle passed through this coordinate point up here on the y-axis, 0, 3. All right, well, sine theta, when we think about sine, we think about y values. So basically this circle is along the y-axis and its diameter is 3. So it's going up towards 3 and its diameter is along the positive y-axis. So I want you to just kind of keep that in mind because again, we're trying to look for patterns to shorten the work for graphing polar equations. So now let's look at some of the most common ways that we can use polar equations to graph circles. We can have a polar equation of the form r equals a, where a is just some number. In that case, what we have is a circle centered at the origin with a radius of a. So in other words, this coordinate point here is going to be at a comma 0, and up here this would be at 0a. This would be over here at negative a 0, and then down here at 0 negative a. If I have r equals a cosine theta, so the cosine function is there, and we think the x-axis when we think about the cosine function, then we're going to have a circle that's shifted along the x-axis, and the diameter is going to be along the x-axis starting at 0 and ending at the value of a. And we saw in that last example, when we have r equals a sine theta, when sine is involved, we're thinking about the y-axis or y values. So my circle is going to be shifted up or down along the y-axis, and it's going to have one end of the diameter on the origin and then the other end of the diameter at the value of a. Now let's use those to graph these circles. So r equals 3 is a circle centered at the origin with a radius of 3. So here is a polar coordinate system. And so we'd label the polar axis, let's say 1, 2, 3. And so my circle is going to be centered at the origin, oops, with that radius of 3. So that is the graph, r equals 3. So for any angle that I substitute in, I'm going to be a radius of 3 or a distance of 3 away from the pole, because there is no theta in this equation. So it doesn't matter what theta I substitute in, the radius is always 3. And if I want to graph r equals -4 cosine theta, I'm going to have a circle that is shifted along the x-axis because it involves cosine. And so if I go ahead and recognize that negative right there, -4, that means that one end of the diameter is going to be at the origin or the pole, and then the other end of the diameter is going to be on the left side, the negative x-axis, 4 units away. 1, 2, 3, 4. So right here is going to be the other side of the diameter. So now I'm going to go ahead and create a circle. I know I'm sort of cheating here because I'm using an iPad to create my circle with the diameter of 4 that is shifted to the left along the x-axis. Now let's look at some other polar graphs. This one is called a cardioid. And what it looks like is kind of a heart shape. This one's on its side and this one's upside down. So hopefully you can see the connection to cardiothoracic surgery, heart surgery, cardioid shaped like a heart. And the equation looks like either r equals a plus or minus a cosine theta and r equals a plus or minus a sine theta. So what these have in common here is that this number is the same as this number. They're both a. And so this number is the same as this number. They're both a. They're equal to each other. And so again, they form this heart, but the ones that involve cosine theta are going to form this heart shape that's sort of oriented to the right or left. But if it involves sine theta, it's going to be oriented up and down. So the way I remember this is that because a equals a, they're meant for each other, and that's why it forms a heart. Now, the next interesting graph of a polar equation is called an inner loop limaçon. So the equations look like r equals a plus or minus b cosine theta. So these aren't the same value. And the relationship is that a is less than b. So this number in front is less than b. And what's going to happen is it looks like a cardioid, except there's a hole in it. And so what I like to do is think about, okay, well, a is less than b, the number in front is less than b. So I like to be silly about it and say, well, if when a equals a, it's a heart and they're meant for each other. If a is less than b, then they're sad because they're not compatible for each other. And so that's why there's a hole in their heart. And if we have a plus or minus b sine theta, when a is less than b still, we still have that cardioid shape with a hole in it, an inner loop limaçon, but now just that orientation is that it's more up and down along the y-axis instead of right and left along the x-axis. And now, finally, we have what's called a dimpled limaçon. So if my equation is r equals a plus or minus b cosine theta, but this time there's a different restriction on the relationship between a and b. So it's very specific. This one says a is greater than b. So this time the number in front is bigger, but not too big. A is less than 2b. So this number in front is bigger, but it can't be more than twice as big. That's the restriction here. So another way to think about this, you might see in other textbooks or resources, if I think about dividing all three parts of this by b, then we'd have 1 is less than a over b is less than 2. So I divided b over b, a over b, and 2b over b is 2. So this is another way to think about the relationship. So a over b has to be between 1 and 2. So again, A is bigger than B. And so if we go with my silly analogy here, so this number in front, A, is bigger, and that's because the tip of what would have been a heart has moved on, right? They've moved on from the relationship. I know, it's pretty silly, but it's the way I remembered it when I was learning how to graph these. So instead of, I'm kind of going to draw it back into a cardioid. Instead of a cardioid, which kind of comes to that point like a heart, right? It has moved on. So now it just forms this little dimple. And of course, the other version, r equals a plus or minus b sine theta. So this is, because it involves sine, more oriented up and down, versus the one that involves cosine is left and right. Let's look at an example. Let's graph r equals 2 minus 2 sine theta. So here, 2 and 2, they're the same value, so they are meant for each other. This is going to form a cardioid. And because sine is involved, it's going to be either up or downward facing. So here, I kind of use a combination of plotting points and then remembering the shape. So again, it's either going to be sort of this upside down looking heart or this right side up looking heart. So what I'm going to do is just plot the quadrantal angles. I'm going to go ahead and substitute in 0 and pi over 2 and pi and 3 pi over 2. I may not even need all of those, but if I plug in the quadrantal angles and plot those points, I can figure out which one it's going to be. If I substitute in 0 as an angle for theta, I'm going to get 2 minus 2 times 0, and so 2 minus 0 is 2. So at the angle 0, I'm going to go 2 units towards the 0 angle. Then pi over 2. So sine of pi over 2 is 1. So I'm going to have 2 minus 2, which is 0. Okay, well that's going to get me back to the pole. So at the angle pi over 2, I don't go anywhere. I just stay at the pole. When I substitute in pi, sine of pi is also 0. So 2 minus 0 is 2. So at the angle pi, I'm going to go 2 units towards pi. That's going to bring me right here. And so at 3 pi over 2, sine of 3 pi over 2 is negative 1. So 2 minus 2 times negative 1, that's 2 plus 2. That's going to give me 4. So I have 3 pi over 2. I'm going to go 4 units towards, a positive directed distance means go towards, 1, 2, 3, 4 units towards 3 pi over 2. So it's going to be this nice looking heart, right? So it's going to be sort of this shape here, and there's symmetry. And so I'm going to try my best here to make it look like that symmetric cardioid. Now, there's one other way we can think about how to graph these polar equations. And so what we're going to do, sometimes what is taught, is to think about r equals 2 minus 2 sine theta instead as y equals 2 minus 2 sine x for a second, and graph this on an xy plane. So in other words, I'm going to do a real quick sort of sketch here of y equals 2 minus 2 sine x. So the inputs are x, the outputs are y, and the key angles are 0, pi over 2, pi, 3 pi over 2, and 2 pi. So we're remembering this from our trigonometry classes. And I'm going to label 1, 2, 3, 4 on the y-axis. And then I'll go down to negative 2 on the y-axis. And we're going to do a quick sketch here. So sine x, if we remember, looks like a wave function. It starts at the origin, and then it's going to go up to the amplitude 1, and then back down to pi, and then down to 3 pi over 2 negative 1, and back to 2 pi. That's the regular sine function. Okay, well, what if it has a 2 in front? If it has a 2 in front, that's going to affect the amplitude. So this is just regular sine x. 2 sine x is now going to make it go up to 2 and then down to negative 2. So this is going to be 2 sine x. What does this negative right here do? That's going to flip it. So now this 2 sine x function is going to be reflected over the x-axis. So that's going to look like this guy right here. So this one is negative 2 sine x. And then that 2 in the front, that's going to be a shift up 2 units. So now this reflected negative 2 sine x graph, if I shift it up 2 units, it's going to look like a final graph. It's going to start right here at 0, 2. It's going to go ahead and touch the x-axis at pi over 2, and then come back up at pi to 2. Then it's going to go up to 4 at 3 pi over 2, and then back down to 2 pi 2. So this is my final answer for graph anyways of y equals 2 minus 2 sine x. So I'm going to erase all the other parts because I don't want to have it cluttered up. I just wanted to do the quickest review of how to graph my trig functions there. All right, so here's my graph, and now it was graphed thinking about it as y as a function of x, but let's go ahead and now think about the horizontal axis as theta and the vertical axis as r. So these outputs are directed distances and the inputs are angles. So what we can kind of do is think about how between 0 and pi over 2. Well, at 0, the radius is 2. So at the angle 0, the radius is 2. And then what's happening between 0 and pi over 2 is that the radius is decreasing. So what I want to kind of notice is that right here at 2, as I move along in angles, right, as I move from 0 to pi over 2, what's happening to the radii is they're shrinking. So it started out with a radius of 2, and then the radii are getting smaller and smaller and smaller, and they're headed back to 0 at pi over 2. And then between pi over 2 and pi, the radii increase. They go back to 2 symmetrically, right? So from pi over 2 to pi, my radii start increasing and they go back to a distance away of 2. Okay, so now between pi and 3 pi over 2, those radii are still increasing. They're going to go all the way to 4, right? The output, the radius is 4. So between pi and 3 pi over 2, as I move from the angle pi to the angle 3 pi over 2, my radii are going to increase. So the distance from the pole was 2, and then it's going to get bigger, right? Like 2.1, 2.2, 2.3, 2.4, and so on and so on. They're going to get bigger and bigger and bigger and bigger all the way till 4. That's the biggest they can get. So now, finally, between 3 pi over 2 and 2 pi, the radii start decreasing, but they go back to 2 and symmetrically, right? So there's the symmetry happening between pi and 2 pi. So the radii were at 4, and then they start to shrink on down until I return to 2 pi. 0 is the same as 2 pi, so we're finishing that out. So it's kind of this unraveling, if you will. So we're looking at this output value as the radii as I move along theta, but moving along theta is moving along the angles. So it is worth it to talk about it because when we get into polar area, the calculus of polar equations, we do want to think about things in this counterclockwise direction. When we think about moving angularly from 0 to different angles, pi over 2, pi, 3 pi over 2, etc. Now, is it the most efficient way to graph? It would be quicker if we just learned the shapes and then plugged in a couple of angles, but going through this process does kind of help understand there are different ways and how to connect the rectangular equation and graph to the polar equation and graph. All right, now let's graph r equals 2 minus 3 cosine theta. So the a value is less than the b value. The number in front is less than this second number. So if it's less than, like I said, less than, all sad, there's a hole in their heart. So this is going to form that inner loop limaçon, like a cardioid with a hole in it. And because cosine is involved, it's going to be sort of oriented more left and right. So my graph is either going to look like, again, a cardioid, but with a little hole in it, this direction, or sort of this direction. And to determine the shape, we're going to just plug in the quadrantal angles. So let's substitute in 0, pi over 2, pi, and 3 pi over 2. All right, so starting with 0, cosine of 0 is 1. So I have 2 minus 3, so I have -1. I know I'm doing some mental math here on the trig, so make sure we're practicing our trig, especially of the quadrantal angles. Pi over 2, cosine of pi over 2 is 0. So here I'm just going to have 2 minus 0, or 2. We'll plot all these points after. R of pi, cosine of pi is -1. So -3 and -1 is +3. 2 plus 3 is 5. And then 3 pi over 2, cosine of 3 pi over 2 is 0. So this zeroes out, we get 2 again. All right, let's plot these. So at an angle of 0, I'm going to go away from the angle 0 because it's a negative directed distance. So instead of going 1 unit towards 0, I'm going to go 1 unit away. At pi over 2, the directed distance is +2. So I'm going to go 2 units towards pi over 2, up. At pi, I'm going to go 5 units towards pi since this is positive. So 1, 2, 3, 4, 5. It's going to take me right over here to the very edge. And then at 3 pi over 2, I'm going to go 2 units towards 3 pi over 2. So towards would be going down. So hopefully we can kind of see where that inner loop is going to be created. So here it's sort of going to look like this little inner loop going on. And then it doesn't narrow down like this. It does actually have that sort of fattened out shape. So we want it to make sure, oh, that's not great. So do your best to look symmetric. All right. And that's it. That's all we need to do to graph this inner loop limaçon. And let's finish this off with graphing r equals 3 plus 2 sine theta. So the a value is bigger than b. So 3 is greater than 2. So greater than, this relationship has moved on. There's not going to be a cardioid or inner loop limaçon. It's going to have just a dimple. And also 3 over 2 is 1.5, which is between 1 and 2. So we know that 3 is greater than 2, and then also 3 over 2 is between 1 and 2. So this is going to create that dimpled limaçon. And let's find the values by substituting in the quadrantal angles. So let's do r of 0, r of pi over 2, r of pi, and r of 3 pi over 2. Lots of trig practice here. Sine of 0 is 0, so r of 0 is 3. R of pi over 2, sine of pi over 2 is 1, so we're going to have just 3 plus 2, which is 5. R of pi, sine of pi is 0, so we're going to have just 3 again. And then sine of 3 pi over 2 is -1, and so we're going to have 2 times -1, or -2, so 3 minus 2 is 1. So let's go ahead and plot these points. If the angle is 0, we're going to go 3 units towards 0. At pi over 2, we're going to go 5 units towards pi over 2. So we already know that's at the very top. At pi, we're going to go 3 units towards pi. And at 3 pi over 2, we're going to go 1 unit towards 3 pi over 2. So here, this is going to be up and down dimpled limaçon because it involves the sine function. We didn't mention that earlier, but we can see that with the points that we have plotted. So here, I'm going to go ahead and kind of start by creating that dimple. So it's a little bit subtle. And then I'm going to start to plot the rest of my graph, or graph the rest of the curve here. And then I'm going to connect here, attempt to make it symmetric. So it's not a sharp comes to a point, right? It's like a very subtle dimple, right, in the curve over here, down here at the bottom. And so this is my graph of 3 plus 2 sine theta. Another really popular type of polar graph is called a rose curve. So the equation looks like either r equals a sine n theta or r equals a cosine n theta. And we're going to break this down into cases. So if n, the number times theta, is odd, then this is going to create a rose with n petals. So we're calling this a rose, even though maybe it just kind of looks like a simple flower. So it's going to create, again, n petals if n is odd. So whatever this number is, that's how many petals there will be. And then the number in front, A, that's the length of the petal. So in other words, this distance from the pole to the very tip of each petal, that distance there is going to be A. So that means down here, this is going to be at, negative A, just the way that this is shaped here, if we're thinking about this as the x-axis and the y-axis. So this distance is A, but if this is the y-axis, we're down here at negative A. And then over here, kind of the same idea, this distance here would be A, so then if this is the x-axis, this value here is A. And again, the length of these petals over here is a length A. And so if the function involves sine, then one of those petals is along the y-axis, and then if the function involves cosine, one of the petals is along the x-axis. And something that's important is that these are quote unquote pretty flowers. So the roses are equally spaced out in terms of the petals. Now, here's the other case. If n is even, so if the number multiplied by theta is an even number, then there's going to be 2n petals. So there's going to be twice as many petals. And again, A is still the petal length. So here, what I want us to notice, this is kind of interesting, is that if sine is involved, there's actually not a single petal that's sort of going up or down, and there's not actually one going left or right either. So there's not a petal that's lying along an axis at all. But if cosine is involved, then we actually have some petals along each of the axes. And so that's something to keep in mind about sort of the pattern when it comes to these rose curves. Let's go ahead and try to graph now. R equals negative 4 sine of 5 theta. So here, since we have n is equal to 5, that means there are going to be 5 petals since n is odd. And then the petal length is equal to 4. So we're not going to take the negative because we're talking about a length. So the length is just 4. Okay, now, since sine is involved and this is an odd number of petals, one of the petals is going to lie along the y-axis. And so we just need to find where that one petal is, and then we're going to figure out where the other petals would be from there. And so what we're trying to do here is we don't want to necessarily plug in all of the angles. We want to try to plug in an angle to figure out what is going to make this output 4 or negative 4. So what do I plug in for theta to make sine equal to either 1 or negative 1? So what I'm going to try, I'm not going to try 0 because I know sine of 0 is 0. I'm going to try pi over 2. So if I substitute in pi over 2, then I have negative 4 times sine of 5 pi over 2. So let's see, sine of 5 pi over 2, that is actually the same as sine of pi over 2, which is 1. So we're going to have negative 4 times 1, or negative 4. So when we substituted in an angle of pi over 2, the directed distance is negative 4. So instead of going 4 units towards pi over 2, I'm going to go 4 units away from pi over 2. And I was trying to generate that output of 4 because I know that's the length of the petal. So if I can get an output of 4, I know exactly where one of the petals is going to be. So I know one petal is going to head straight down. Now, to construct the rest of this, I want to use the fact that, again, these are pretty roses or pretty flowers. So the petals are equally spaced apart. Now, if we want to be really precise about this, because we know exactly where one is, if we can find the distance between them, we can draw all the other ones exactly where they're supposed to be. Now, how would we go about doing that? Well, the entire unit circle is 2 pi or 360 degrees. So to divide that up evenly into 5 petals, we would just divide by 5. So we would take 2 pi divided by 5. All right, so that's how far apart the petals have to be. Well, it's probably a little bit nicer if we do it in degrees. So 360 divided by 5 is 72. So these petals are going to be 72 degrees apart. So this down here is at 270 degrees. If I subtract 72 degrees, that's going to get me to 198 degrees. So that's, bigger than 180. So we'll just say like roughly right here, 198 degrees is another petal. Whoops, I put it too far. I put it at a distance of 5 away. So it'd be right about here. Here's another petal. If I add 270, I'm going to get 342. So I don't know, maybe about right here. I'm just approximating at this point. And whoops, I did it again. This should have been at 4 units towards 342. And so there's another petal. If I subtract 72 again, that's 126 degrees. So here, I'm going to go ahead and say that's right about here. I did it again. 126 degrees, but the point would be right around here. And then if I subtract 72 again, that's going to be 54. So 54 degrees, a little bit bigger than 45. Put the point right here, and I'm going to draw my petal. So here's my pretty rose curve, right? My petals are evenly spaced-ish, kind of as close as I could approximate these values. Not that it necessarily has to be this precise. We just want to make sure that they look, roughly evenly spaced. Now let's graph the rose curve 3 cosine 2 theta. Now here, n is equal to 2, and because it's even, there's going to be 2 times 2 petals, so a total of 4 petals. The petals doubles, and then the petal length, that's going to be 3. Now here, let's go ahead and recognize that when cosine is involved, if we substitute in 0, cosine of 0 is 1, so we're going to get out that petal length. We're going to get out 3. So r of 0 is equal to 3. So that means that one of the petals is along the x-axis, and we're going to go 3 units towards 0. So one of my petals is going to be right here on the positive x-axis. Well, if there's 4 total petals and they have to be equally spaced, then we're really just dividing 2 pi by 4, which is the other quadrantal angles. So we're going to have another angle, or excuse me, another petal that goes straight up towards pi over 2. That's a length of 3 units. Another that goes towards pi, a length of 3 units. And another that goes straight down towards 3 pi over 2 that has a length of 3 units. We'll wrap up our discussion on polar graphs by looking at a few interesting ones, but we're not actually going to do examples of these. Let's take a look at a lemniscate, which basically looks like an infinity symbol. And the equation for that is r squared equals a squared cosine 2 theta, or sort of this sideways looking infinity here, or like a diagonal one. And that is graphed by the equation r squared equals a squared sine of 2 theta. And then we have this Archimedes spiral, which the equation is r equals theta, where theta is greater than or equal to 0. So it's kind of cool. What we're saying is that the angle is equal to the directed distance. So it starts at 0, 0, and as we increase the angle, the directed distance matches that. So if we increase the angle, the directed distance is getting further and further away, which creates what is called the Archimedes spiral.